Hello, everyone. Welcome to this fourth session of the second part of Beyond Bohm, David Bohm and Philosophy. I'm James P. Barbieri, Associate Program Director here at the Power Center, and I'll be your host for today. As a host, I'm here to help you. So any problems, just let me know in the chat. Before we begin, let me just very briefly go through the guidelines for this call. Firstly, if you can please mute your microphone to ensure good quality audio, but at the same time, we do encourage you all to turn on your camera. The chat is open throughout the call, so feel free to use it to share your thoughts and ideas with the group in regards to all the topics that we're discussing. And also we do have subtitles, live transcriptions. So if you want to see them, you can go bottom of your screen and show subtitles. Finally, this session is recorded for archival purposes and for you all. The recording should be available in a few days when you receive the link. Okay, so we can begin. Today, we are honored to be joined by William Seager. Bill is a professor of philosophy at the University of Toronto in Scarborough. He has been working on the philosophy of mind and especially the problem of consciousness for about 45 years and has published several books, including his recent Theories of Consciousness and the Routledge Handbook of Panpsychism. Today, Bill will be talking to us about consciousness, Bohm, and the quest for intelligibility. And with that, I'll pass it over to you, Bill. Welcome.
Thank you, James. And I want to start by thanking the Power Center. I had the great pleasure of being there in person in June. That's an amazing session. So special thanks to James and Eleanor. Really a remarkable institution. Okay, so I will begin sharing my slides. I won't know what to say unless I can see them. Okay, share screen. There we go. Hopefully you can see the title page. I've changed the title a little bit. For some reason, I thought hunt rather than quest suited Bohm down to earthness better. Doesn't matter very much. Anyway, I want to talk today about a trail that ends up with David Bohm's views. I think it can be understood as a long-term quest for intelligibility. And by long-term, I mean centuries and centuries. So let's think about the project of metaphysics itself. An ancient subject which Wilfrid Sellars in the 60s described this way. The business of metaphysics is to see or understand how things in the broadest possible sense of the term hang together in the broadest possible sense of that term. Really, it's just trying to find a picture, a comprehensible picture of the structure of the entirety of reality. Really, I don't think anybody but philosophers try and do this, and very few philosophers anymore actually are trying to do this. But everyone, I think, has some natural feeling for this project. We really do want to understand how the whole thing hangs together. And it's natural to think we should use our very best source of knowledge when we engage in this project. And it's also natural to think that the very best source of knowledge we have is science. And with respect to the metaphysical aspects of these questions, physics, especially fundamental physics. Now, this is already controversial, and I don't want to give the impression that this way of thinking about physics stands without criticism. There is a strong anti-realist contingent in the philosophy of science that would deny that science provides the best route to understanding fundamental reality. There's a kind of fear or worry about the hegemony of science in the world. Sometimes what people call scientism raises its head as a problematic position where science rules over all other modes of thought. So I certainly don't want to suggest I agree with that, but this picture is, I think, largely physics' own self-image. Here I have a quote from a working panel that was charged with explaining why America should send money to the Large Hadron Collider, which of course is not in America. And in this document that was produced, and it was successful in getting funding, here's one answer. It's important to join the LHC because it would promote recognition by key audiences of the value to the nation of particle physics because of its unique role in the discovery of the fundamental nature of the universe. There we have the picture that, yes, okay, it's high energy physics. That's where we find the fundamental nature of the universe. So I suggest let's just, even if you don't believe in this or have grave doubts about it, let's go with this for now, because one obvious project would be to take what we know from science and use it to figure out how everything hangs together. So let's start with that self-image. Now, if you think about the project of metaphysical understanding, it's truly ancient. It blends in, I think, with early religious thought, proto-religious thought. And one way to picture this is as the transmutation or the use of familiar concepts in unfamiliar surroundings. So we take ordinary concepts from the ordinary world and we extend them. I say, yeah, usually too far. But there are lots of examples from the history of philosophy and science. Here's one, atomism. Beautiful idea. What is it? Well, you extend the concept of part-whole composition, which we see in the world around us everywhere, and you add to that how we notice material bodies interacting. They bump into each other and move. So we're familiar with that, and then we say, well, wait a minute, maybe everything is like that. And inside every material object are the zillions of little tiny material objects, and they're just moving around, bumping into each other. That's one traditional metaphysical picture. There's another one that's interesting, what I've called here intentionalism, and that's where we take the purposeful actions that we see in people around us, and we translate those into the rest of the world. So we extend our notions of the belief and goal-directed and desire-satisfying behavior. And so then we pretty soon are talking about the moon wanting to go around the earth and things like that. I suppose ancient animism might come from this. It's another way and very different way of producing a large-scale metaphysical picture. The atomistic picture gets transmuted when you think about moving towards science. Ancient atomism is not really a scientific theory. A scientific metaphysics will, I think, vastly extend some core picture of how things work in a restricted domain and try and extend that over the entire world. The notions may stem from the quotidian concepts that we have, but there's some scientific picture that's at work and then gets extended. Now, if you follow this route, you face a problem. will almost always be the case. It has always been the case that not all the phenomena that we want to understand seem to fit in to one of these restricted pictures of the world. And then you either have to have some theory of emergence, or you are going to have to deny the existence of the phenomena. And both of those things happen frequently. For the things we will accept as emergence, we think we can explain them in terms of our underlying model somehow. We just need a better picture of how things work. But often enough, we cannot explain some feature. Then it's time to say, oh, that's just an illusion. An old example, the illusion that the sun moves as it rises. It sure looks like it. But we say that's an illusion. It's not true that the Earth is stationary. It only looks that way. We can reject that. We don't have to explain that. We can just reject it. These dual moves, emergence or illusion, happen over and over again. Now let's go through our strange trail, which begins with the mechanical worldview, stemming from 17th century, the birth of science, the incredible century of geniuses. I forget, someone said it must have been that the Earth was passing through some cloud of substance that made people smarter, and hence the 17th century flourishing. Well, I don't expect that's true, but the 17th century is incredible for scientific development. Something like a dam broke, right? Just huge. The mechanical worldview is something which comes from our basic idea of material bodies. It says everything that happens should be explained and can be explained in strictly mechanical terms. Of course, it's going to be really complicated. We won't be able to actually write down all the interactions, but that's the picture. And what are the interactions? Well, just contact and motion. Objects move and they continue in their motion until interrupted. The interruptions will be contact, and then objects will change their direction. Now, Leibniz will figure frequently here today. Here's Leibniz's view of the mechanical world picture. He says, the mechanical view explains everything in the nature of body through number, measure, weight, or size, shape, and motion, and teaches that nothing is moved naturally except through contact and motion, and so teaches that in physics, everything happens mechanically. That is, intelligibly. The idea being, if that's everything that's happening in the natural world, we have a fundamental way of understanding it. We know what's going on. The complexity will outrun our ability to describe in detail, but that's not so surprising. The basic picture, though, is clear and intelligible. Now, the mechanical view did not last very long. At least it didn't last very long as a practice. I think its aspirational side still haunts modern science. For example, almost co-extensive with the birth of the mechanical view, you get Newton introducing a completely mysterious, inexplicable, instantaneous force of gravity. It's completely at odds with the mechanical picture. It's not by contact. It happens no matter how far apart objects are. Terrible thing. There's a nice letter Newton writes to somebody who basically, Newton says, I don't think anyone who isn't a blockhead could actually believe my theory. But he says it works. So someday we'll figure it out. Leibniz, of course, denied Newton's picture. So completely unintelligible action. He tried to produce a mathematical theory of gravitation based on vortices, and he actually made some good progress. He could deduce Kepler's laws from his vortex, but it doesn't work. Really, it can't work. It was proven that you can't do it with vortices later. Anyway, Leibniz also polemically attacked the Newtonian style of physics. He called it barbaric physics. And he says about it, people love to be returned to darkness and returned to chimeras or archae or plastic intelligences, and return to occult qualities or to scholastic faculties. But he goes on and he says, but since those words are in bad repute, changing the name, they call them forces. But forces for Leibniz are just more of these mysterious, ghostly things operating outside the mechanical picture, completely inexplicable. The quest for mechanical intelligibility, at least this aspect of it, was never abandoned. Maxwell would produce mechanical models of the electromagnetic field. And in any event, the field picture eliminates the action at a distance side of things. So at least you get rid of that aspect of unintelligibility. And maybe Einstein was partly motivated by worries that an action at a distance. And in the general theory, he eliminates gravitational action at a distance. But the demand for purely mechanical explanations was given up. The world couldn't be explained just in terms of motion and contact. Well, is that the end of the story? People gave up looking for intelligibility? Obviously not. We have a switch to a different kind of intelligibility. I'm going to call it mathematical intelligibility. Here, this famous picture, here's the famous Pythagorean theorem. It's a proof. If you think about this picture, you will see the Pythagorean theorem is obviously true. That's a kind of intelligibility. So I want to distinguish the mundane intelligibility we've been talking about, which is understanding things in terms of ordinary concepts extended into a new domain. And add to that mathematical intelligibility. We have for mundane intelligibility all the models of the mechanical picture, the pool table as a model for how atoms work, things like that. Mathematical intelligibility does begin from the same spot. I think mathematical intelligibility begins with the observation that this mundane intelligibility can be represented mathematically. You can go play computer pool on the internet. The computer is able to mathematically represent what's happening on the pool table. This is only the beginning, though. I think it's Galileo who opened this door. He's the icon of the insight of linking mundane and mathematical intelligibility. Here's a famous quote from him where he says, "The universe is like a book, but one that cannot be read unless one first learns to comprehend the language and recognize the letters in which it is composed. It is written in the language of mathematics, and its characters are triangles, circles, and other geometric figures." So the mathematical picture of the world begins in this mundanely intelligible way. So you have some nice model that is intelligible in terms of ordinary concepts. Then you discover that you can represent those mathematically and get a much more precise picture of what's going on. So there is a satisfying correspondence between the intuitive understanding and this precise representation, which also strips away everything that's inessential. If you think about modeling the pool table, the color of the pool balls has nothing to do with their motion. It can be just eliminated from the program. Of course, it can't be eliminated from the scoring, but that's another problem. What's perhaps surprising, it surprised many people, is that this new way of representing, where you transmute this mundane understanding into a mathematical picture, then suggests new phenomena, maybe phenomena that have never before been observed. It's almost as if we get more out than we put in, or sometimes, as people say, the mathematics is smarter than I am. There's a famous paper by Eugene Wigner, The Unreasonable Effectiveness of Mathematics in the Natural Sciences. How come mathematics works? How come when we represent some aspect of the natural world using a mathematical representation and then do some pure math to deduce some extra or additional feature, and then we go and look, and sure enough, in the world, we find the phenomena that the mathematics suggested. Why should that work? Why is nature so amenable to being represented in mathematics? An excellent question, still debated. Why, or even if that's an issue. Now so here I've tried to make a picture where we take our mundane understanding, we map some mathematics onto some aspect of it, and then get a mathematical representation of the same phenomena, which then we can extend. But as we develop a faith in mathematics, this need to coordinate the mundane and the mathematical representation begins to disappear. The mundane side gets left behind. And we might call this the search for pure mathematical intelligibility. And here's an amazing example of this. Emmy Noether's theorem, there she is, one of the first women, I think, to teach math in German university. Her theorem provides a mathematical account of why quantities are conserved, such as energy. In general, for any continuous symmetry, there's an associated conserved quantity, a kind of mind-blowing connection that no one, certainly independent of this work, you would never have guessed that would be true, I think. There's a story about her. I think David Hilbert was her champion for her job at Göttingen. And there was much debate with the senior faculty, all men, of course, very contentious. They thought the idea of having a woman on the faculty was ridiculous. And David Hilbert apparently said to them, "Gentlemen, is this a mathematics department or a bathing institution?" And she was admitted. Here's a very trivial illustration of Noether's theorem. Suppose we have a particle subject to some force stemming from a potential, U of x. And as a hypothesis, we assume that this potential is invariant under spatial transformation. That is, if you change the position, the potential won't change. So ux equals ux plus some delta. Now the force is, by definition, the negative derivative of that potential. And we've just said we've just assumed it's invariant. And so that derivative must be 0. But we also know from Newton's laws that the force can be given in terms of the momentum The change in momentum over time is the force. We've just said that is zero. So if we assume that this is invariant, it turns out that the change in momentum is zero, so momentum is conserved. And there we've just shown conservation of momentum. Noether's theorem works much more widely than that. That's a truly trivial example. Now, it requires a lot of math to set up the framework, the so-called Lagrangian framework, for representing your theories, precise general definitions of what a continuous symmetry and invariance are. We have some kind of ideas about this. Continuous symmetry means no matter how small a change in this variable, the structure of the theory will remain the same. Things like that need to be precisely defined. This can be done. It's mathematical work of a high order. Physicists have taken this idea and really run with it to unbelievable extents. They've taken this idea of invariant symmetries to account for and generate new laws of nature. So this is like Wigner's question, written very large indeed. Of course, to do this, we make assumptions. We make assumptions about what constraints there are on the theories and the laws that we have. So, for example, there's a relativistic constraint. Nothing can move faster than the speed of light. But once we make these assumptions and we get invariance of some symmetry, then laws of physics pop out, which work and be verified. So I want to mention an example which is complicated, but you'll see the point. Don't worry if some of this is unfamiliar. So here we begin with the Lagrangian. Lagrangian is just a formula which kind of gives the dynamics of the system. It's really just, well, simplest form would be kinetic energy minus potential energy. But anyway, we take the Lagrangian of a free spin 1/2 field. That's a field in physics that has intrinsic spin 1/2, maybe the electron field, say. Anyway, we note that multiplying the field state by a unit complex number, e to the IA, makes no change to the physics of the system. It is invariant under this transformation. This group of transformations multiplying by a unit complex number is called U1. So here we have what's called a global U1 symmetry. Okay, so fine, very good. Turns out though, this global transformation changes the whole field instantaneously. That's what we've written down, right? The whole field changes. That violates relativity. Bad, can't do that. So now, instead of doing that, well, we'll try multiplying the field state by something depending on position. So we can make it local, get a local symmetry. So there, instead of multiplying just by this, we make this thing a function of position. Good, now we have a local symmetry. We haven't violated relativity. But now, disaster strikes. Our new form is not invariant. If you look through this, you'll see it. An extra term now suddenly has appeared in the Lagrangian. It looks like that. A derivative term, negative derivative term. It looks like disaster. How can we restore invariance? Well, consider another field. Now this is a free massless spin 1 field. Spin 1 field, maybe like photon field. We follow exactly the same trail. We find the Lagrangian for this field also has a global symmetry, which we must get rid of. And trouble arises when we try to make a form with local symmetry. Now, in this case, local symmetry is achieved, but a term must be added again. We must add a derivative, positive derivative of some arbitrary function. I'm stealing all this from Schwichtenberg's book, which is an amazing book about all this stuff. So you will have I'm sure you've noticed something here. The relation between the two terms. Wow, one's a minus, one's a positive. They have the same form. Otherwise, if we put the two fields and couple them together, the term in the spin 1/2 field is canceled. And the resulting combined Lagrangian turns out to be the Lagrangian for quantum electrodynamics, which from Noether's theorem reveals that electric charge is conserved. Schwichtenberg says we're able to drive this Lagrangian simply by observing internal symmetries of the Lagrangians describing the free spin 1/2 fields and the free spin 1 field. Now, this is a supreme example of mathematical intelligibility that has left mundane intelligibility far, far, far behind. I'd say a magnificent mathematical intelligibility. And it's even more remarkable, we can reenact this search for local symmetries using this methodology, group theory methodology. And using it, we find the physics of the nuclear force and the physics of the nuclear strong force. These can be just kind of derived from this from these basic mathematical principles. However, you say, well, let's keep going, there's unlimited number of groups in group theory, let's just keep going. No, it doesn't, it suddenly stops working. Trying to go further to add gravity or find new forces fails. Schwichtenberg says, why is there no fundamental force following from SU4? Nobody knows. So an amazing story of mathematical intelligibility. Now, I want to talk about quantum mechanics a little bit, and again, a kind of mathematical intelligibility. This Noether's theorem is understandable. You can see how it might work, the basic idea of the theorem. Quantum mechanics seems to pose deeper problems. Maybe you might think we need to cut the distance between the highly abstract mathematical structures and the experienced world by applying a more specific theory. But in this case, the theory involved is quantum mechanics. And that is not exactly a happy home of mundane intelligibility. We all know that how the material works according to quantum mechanics is extremely bizarre. So I want to give a little example, maybe my favorite example of how weird quantum mechanics is. And this is the quantum Bohm testing procedure. You imagine, it's a pure thought experiment. You imagine you've got a bunch of bombs. You would like to test whether they're duds or good bombs. But unfortunately, any interaction with a good bomb causes it to explode. So yes, you can say that was a good one, but then you don't have your bomb anymore. If you still got the bomb there, then it was a dud. But you would like to, you'd still like to say, is there a way we can test whether we've got a good bomb without destroying it? And using quantum mechanics, the answer is yes, there is. Here, the machine to do this is an interferometer, a Mach-Zehnder interferometer, which looks like this. You see the beam comes in at the input, and the first beam splitter, 50% of the photons go one way, 50% go the other. Then they hit those mirrors and bounce towards the second beam splitter, where they can either go through or be reflected. However, if you set up the structure of the beam splitter just right, the distances of the arms, you will only ever get a result at D1, the top detector there. there's destructive interference for D2 and constant. D1. We've got our super sensitive bombs. How can we test them? Well, what if we put a bomb in one of the paths? Now, it's set up this way. If the bomb is a dud, it's just got a mirror on it and the photon just passes right through. It's as if the bomb wasn't there. If the bomb is a good bomb, and if the photon is in arm 1, then the bomb explodes when the particle hits it. What happens if the bomb is good, but the particle goes in the other path? Well, then we would know that that bomb was good because we will get sometimes a result at D2. The interference is broken because we put a detector into the system. A well-known quantum effect, right? If you like the two-slit experiment, this is basically like the two-slit experiment. If you put a detector in to see which slit the light goes through, then you lose the interference pattern. This is what's happening here. So half the time with a good bomb, you will know you have a good bomb without exploding it. You will know it's a good bomb, even though you will have never interacted with it. No particle ever interacts with it. Now, this is extremely peculiar, really, if you think about it. You say, well, what's going on? Very hard to understand. Very strange world we live in where that happens. Mathematically, it's not hard to understand. We have a superposition of the two paths. And when we have the bomb in the path, we get a slightly more complicated superposition where each path is entangled with the bomb. And when you get, if you calculate this out, you will find that you will cancel the interference terms just as we suggested. And that means sometimes you will get a particle at D2. This is mathematical intelligibility, easy to work out. But how does it work? Physics, you might say, is supposed to tell us, well, what's the physical interpretation of this? And that's hard to produce. Feynman, here's a famous quote, I've changed it a little bit, but only to satisfy modern sensibility. Feynman says, I can safely say that nobody understands quantum mechanics. I'm going to tell you what nature behaves like. If you will simply admit that maybe it does behave like this, you will find it a delightful, entrancing thing. Do not keep saying to yourself, if you can possibly avoid it, how can it be like that? Because you will get down the drain into a blind alley from which nobody has escaped. The blind alley, which Feynman sometimes derisively called philosophy. He says, nobody knows how it can be like that. Well, what quantum mechanics is trying to tell us about the world does remain very mysterious. And that's why we have a plethora of interpretations of quantum mechanics. Quantum mechanics, we want to understand. We're not quite happy purely with the mathematics. We have mathematical intelligibility, extremely high order. That somehow is not satisfying. We would like to know how the world works such that that mathematics describes it. So here, David Bohm, maybe he's right. He says, the entire universe must, on a very accurate level, be regarded as a single indivisible unit in which separate parts appear as idealizations permissible only on a classical level of accuracy of description. So maybe this Bohm experiment, the problem is you think it's made of parts. And if you think of it's made of parts, then you can't figure out how one part can communicate with the other part. But maybe that's the wrong picture. This is quite a radical picture of the nature of reality, however. Here's another possibility. Eugene Wigner said, laws of mechanics cannot be formulated without recourse to the concept of consciousness. This is also a very radical view. The idea that somehow consciousness is necessary for the operation of quantum mechanics seems very peculiar and seems to threaten that consciousness must be everywhere. And of course, that seems like a very strange view indeed. Or we have Niels Bohr, and he says, maybe the strangest of all, there is no quantum world. There is only an abstract quantum physical description. It's wrong to think that the task of physics is to find out how nature is. Physics concerns what we can say about nature. I guess what we can say about nature at the observable level. This is a kind of defeatist picture. It's a possibility. How could it be that there is no quantum world, though? That seems to be what everything is made of. Now, I want to turn back to Leibniz as a guide for a third kind of intelligibility that now is looming. You can't understand quantum mechanics mundanely. It just does not fit into any of our ordinary concepts of understanding the material world that we're familiar with. But maybe there's another kind of intelligibility, which I'll call metaphysical intelligibility. Here we have Leibniz in the famous scene in the garden where Leibniz has just announced that there are no two things in nature that are exactly the same. And the nobleman there says, that's ridiculous. Look on the trees, the leaves. They're all the same. And Leibniz says, go and look, bring back me two leaves that are exactly the same. And of course, can't actually be done. No two leaves are exactly the same. Leibniz has, of course, proved that to his own satisfaction, but he was able to send the nobleman away and could spend time with the noble ladies. Now, in quantum mechanics, there just doesn't seem to be any intuitive physical model. We talked about that Bohm detector, the magic Bohm detector, and innumerable other puzzles that quantum mechanics poses to common sense understanding. So here we have this disconnect between mundane intelligibility and mathematical intelligibility. And I think that's why you have all of the interpretations of quantum mechanics. They're all striving for something more, which really is metaphysics. What they're trying to do is produce a metaphysical picture of reality by which we could explain the bizarre features of, in this case, quantum mechanics. Now, Leibniz is like a perfect model for this, albeit one from centuries ago. Leibniz strongly endorsed the need for mundane intelligibility. This is what's interesting about him. He, for the physical world, was a mechanist. He believed that everything in the physical world had a mechanical explanation, but he did not think that that meant you were finished with your job of understanding the nature of the world just when you gave the mechanical picture of it. There's more work to be done. There's still a metaphysical job, giving the metaphysical intelligibility. Now, interpreting Leibniz is difficult, and there's controversy about whether and to what extent he modified his views or replaced them over the years, or maybe merely developed them. I say it's controversial. In what we might call his middle period, he seems to have regarded the material world as something that existed in its own right, independent. And within this material world, mechanical explanations reigned supreme, and they were complete. In 1678, he can write, "I recognize nothing in the world but bodies and minds, and nothing in bodies insofar as they are separated from mind, but magnitude, figure, situation, and changes in these, either partial or total. Everything else is merely said, not understood. Sounds without meaning." That's, of course, he's talking about the things other people called forces, sounds without meaning, ghostly aspects. But he came to have metaphysical doubts about this. This is the period in which Leibniz enunciates his pre-established harmony solution to the mind-body problem, where you have your mechanical physical world working by mechanical principles, and then you have another world, the world of consciousness. They're completely independent, but like two synchronized clocks, they're running along in parallel. But he began to have metaphysical doubts about this picture. Now, here too, we have controversy about Leibniz. Everyone knows about Leibniz's monadic philosophy, but as he was approaching, I think, the view of monadism, which is a kind of idealism, he begins with what I would call a kind of panpsychism, and which what he calls something soul-like is added to or stands under matter. And why did he think you needed to do this? Basically, matter is infinitely divisible. And this, he thought, entails a kind of dissolution to nothingness. He writes, if matter is infinitely divisible, then one can never arrive at the simple unities that must exist at some ontological ground level. This matter is also entirely passive. It only reacts. Therefore, Leibniz thinks requires a principle of activity to become real. What he called primitive force, which is an all-corporeal substance as such, since I believe that a body entirely at rest is contrary to the nature of things. An interesting anticipation of modern physics. Primitive force, he says, is nothing but the first entelechy. It corresponds to the soul or the substantial form. But for this very reason, it relates only to general causes, which cannot suffice to explain phenomena. So he's not going to get rid of the mechanical explanations. The physical material world will still be completely explicable mechanically, but it needs this background metaphysical underpinning, really, to give it reality. Now, finally, in Leibniz's last move, if we want to think of him as moving from doctrine to doctrine, he eventually sees that matter in the material universe is merely phenomenal. There is no independent existence of a material world. It's merely what he called a well-founded phenomena supervening on the perceptions of soul-like monads. Because once the monadic perceptions are in place, if you think Leibniz's monads, each one is like a mind undergoing a sequence of perceptions, feelings, thoughts, for more important monads like us, the sequence of mental states. And once all of these perceptions are in place, there's actually no need for a separate material world. The material world is kind of a mere reflection of the system of perceptions. Each monad would see the world from its own perspective, so to speak. And you could abstract from all of the perspectives a kind of picture of a material world. Leibniz, just as an aside, an interesting one, I think, though, Leibniz believed that all relations were reducible to properties. A very interesting thesis. Would be a simple example would be if I say, here's a relation, A is taller than B. Well, that relation depends on the height of A and the height of B. It's nothing more than a statement about those two heights. The reducibility of relation also leads to the monadic picture. But anyway, I don't want to explore Leibniz's philosophy any more than this, merely to point out that you have this pathway from the first mechanical understanding to this need to have a metaphysical picture which underpins it. This is, I think, not just Leibniz's problem. This is a general problem that we all face. There is a need for a metaphysical intelligibility, even where mundane and mathematical intelligibility line up. But think of the situation we have in something like quantum mechanics. So the mathematical intelligibility comes without any mundane intelligibility to match it to. It stands by itself and seems entirely mysterious. I say we have lost any hope that mundane intelligibility will be preserved. And I think, again, this is why we have such a huge number of distinct interpretations of quantum mechanics. If you look on the Wikipedia page, there's more than 18 interpretations of quantum mechanics. They all are an attempt. They're not, by and large, they're not an attempt to do new science. They're basically an attempt to explain the metaphysics of quantum mechanics. There are a huge number of interpretations, which I cannot go into. I want to mention some as we come up to Bohm. So here's one interpretation which leans towards the new science side. The Ghirardi-Rimini-Weber theory of, as it were, punctuated wave function collapse. I'm sure you're all aware one of the big problems with quantum mechanics is the basic structure of the theory proposes that the wave function evolves deterministically according to the Schrödinger equation. How then do we ever get a particular measurement result? Well, the classic answer is when an observation is made, the wave function suddenly collapses into one of its eigenvalues, eigenstates. This collapse is bizarre, instantaneous, apparently, very disturbing feature in an otherwise deterministic theory. GWR, they deny that it's the act of observation that collapses the wave function. It's really more a matter of the mass or structure. As this increases, the chance of a collapse increases proportionately. So if you get any kind of a, well, even still very small, above the truly micro level, the wave functions will collapse very quickly. Whether this interpretation is successful is very controversial. And on its own terms, it actually seems to leave wave function in place, thus not really solving the problem. It leaves us with low amplitude elements of the wave functions, but those don't seem to be nothing. So there's a problem there. I think Penrose's view also, where it's the gravitational size or the gravitational force of the system, which somehow induces a collapse, similar to this. Here's another interpretation, very metaphysical, makes no new prediction about the outcome of any experiment. GWR in principle does. The interpretation of Everett is tricky too. I don't think he ever actually talked about worlds, but I think he talked about branches. Anyway, the general picture we all know is when superposition collapses, as traditionally understood, what we have instead is a splitting where two branches form, two or more branches form, and these branches go on to proliferate as more interactions happen, and there will be this infinitely foliating wave function of the universe. I've always wondered whether Everett actually believed this, or whether he just wrote it as an interesting idea. I'm not sure. Here's a sad story, though. His daughter committed suicide, and the suicide note read, among other things, "Goodbye, Daddy. I'll see you in another branch." And I guess he'd been telling his children of this view. I think maybe he really believed it. In any case, the advantage of Everett's theory is that you have the unitary deterministic evolution of the quantum wave function of the universe, smoothly continues. There's never any collapse at all. The interpretation has some big problems. You have to understand why we end up finding ourselves in a world that looks classical. There'll be lots of branches that aren't classical. And it has a hard time with probability. I don't think I want to go into this. Well, let me just mention, if you think about setting up a quantum system, a quantum coin that come up heads or tails, and we set the amplitudes 99% heads and 1% tails, the theory is still saying there's two branches. Where'd the probability go? What are the amplitudes doing? So this needs to be understood in the many worlds theory. But I think the basic problem is one that's common to these interpretations. What is the nature of the world itself according to these pictures? The mundane intelligibility of the mechanical worldview just took at face value this quotidian perception of matter as a massy, impenetrable, movable stuff, and then just extended that into a mathematical elaboration that was extremely successful. Now, in quantum mechanics, we have this extremely successful recipe for determining what we are likely to observe, but these recipes are couched in terms of entities which are not easy to understand. They certainly have no mundane intelligibility associated with them. So the wave function of the universe is going to be something with a huge number of dimensions, infinitely, I presume, highly dimensional abstract space. What is that in terms of the nature of the world? So what we're being asked to believe about the nature of the world is quite unclear here. You might think, well, to repeat myself, we would hope that the physics would tell us what is the physical significance of these. What do they mean physically? And it is very hard to see that we have any idea what that is. Another possible interpretation then, more like Bohr, I think. What if we give up this idea? What if there's only mundane intelligibility? What if we take experience as itself fundamental? Now, there's a theory in quantum mechanics called a theory of quantum interpretation called cubism, quantum Bayesianism, that is a view like this. And it says that quantum mechanics is nothing but a mathematical machine for assigning subjective probabilities. That is, quantum mechanics' only job is to tell you what you should expect to observe. That's it. It does not say anything in itself about the nature of reality. It would be a mistake to think that because it tells you what to expect, that you should read the machinery as referring to some hidden away physical stuff or processes. So quantum mechanics is not a description of the world at all. And this is why people say cubism is kind of like Bohr. There is no quantum world, Bohr said. Cubism is sort of similar in this respect. It does leave us with the question, why in the world would I assign probabilities using the quantum formalism? That remains very mysterious. But let me instead talk about the metaphysical side of this, because there's a close link between this picture of cubism and William James's neutral monism. Now, many here may be familiar with this idea. Neutral monism was James's way of getting around the dualism of mind and matter, and said, in fact, there's only one stuff of the world, and it is neither mental nor physical. It's neutral. And one of the proponents of cubism, Christopher Fuchs, he writes, the case cubism makes before the forum is this: what the quantum agent is ultimately doing is hitching a ride with a new kind of ontology or metaphysics, an ontology of all pervasive pan-creative experience. This is supposed to be an allusion to James. Here is Fuchs quoting James, in fact. My thesis is that if we start with the supposition that there is only one primal stuff or material in the world, a stuff of which everything is composed, and if we call that stuff pure experience, here, this is a bad word that James uses. It's not supposed to be mental, and yet he calls it experience. Problematic. But anyway, then knowing can easily be explained as a particular sort of relation towards one another into which portions of pure experience may enter. The relation itself is part of pure experience. One of its terms becomes the subject or bearer of the knowledge, the knower, and the other becomes the object known. Maybe you could understand that way. You'll see this is deep metaphysics. And that we were driven to it, according to the cubist, by trying to understand what quantum mechanics is telling us. Now, to end up, I see I'm running out of time a bit. I want to leave time for questions. Here, let's talk about David Bohm's path and his metaphysical physics. I think it's the same urge. You have this weird theory. You need to understand what it means. You cannot give a mundanely intelligible explanation. So you will look for a metaphysically intelligible account. David Bohm is most famous, probably, certainly among physicists, for showing that a hidden variable quantum mechanics is possible. At the time, it was thought that maybe it had been shown, sort of, that hidden variables were impossible. Not so. So John Bell famously reacted to Bohm. He says, in 1952, I saw the impossible done. It was in papers by David Bohm. And he did. Bohm did produce a theory in which particles could have definite positions and momenta. and evolve deterministically. Some regard Bohm as a throwback to the mechanical world view. David Albert, a philosopher, says the metaphysics of Bohm's theory is exactly the same as the metaphysics of classical mechanics. And Christopher Fuchs says Bohmism represents a hopeless return to the womb of classical physics. Yuck. I think nothing could be less true. These two remarks just seem completely opposed to what Bohm actually thought. His view is extremely distant from a reversion to classical physics. And this is obvious, really. The quantum potential is added to the theory, at least to the understanding of the theory. And this makes a completely distinct kind of picture of how particles operate. The quantum potential is kind of like a guiding wave, and it has two crucial properties, which are completely opposed to the linchpin idea of the mechanical view. Here is the mechanical view. Given the position and velocities of all the particles at one time, the history of the universe is completely determined for all other times, past and future. The Bohmian picture is not at all like that. Here we have, I think, the core of this picture. This is from a book by Hiley and David Peake, founder of the Power Center. The quantum potential does not produce, in general, a vanishing interaction between two particles as the distance between these particles becomes very large. The two distant systems may still be strongly and directly connected, completely at odds with any picture of mechanical interaction. The quantum potential cannot be expressed as a universally determined function of all the coordinates of the particles. The particles are not really calling the shots here. Rather, it depends on the quantum state of the whole system or of the system as a whole. This means that even if at some time the positions and momenta of two sets of particles are the same, but they are in different quantum states, their subsequent evolution can be very different. Again, completely at odds with the mechanical picture, and also completely at odds with those quotes that I gave criticizing Bohm. Bohmian's view adds this extra dimension to reality, so to speak, an extra parameter that governs the motions of the particle. Now, I think there's a kind of comparison with Leibniz. Leibniz needed this extra feature, which he called active force. He called it a soul-like property of matter. And so Bohm appeals to this extra active power. Of course, for Bohm, we also have an empirical motivation, which I think is absent in Leibniz. You remember Leibniz believed everything in the world happened mechanically, and this metaphysics was a backdrop. In the case of Bohm, the active power is physically real. It has effects. Bohm attempts, I think, to achieve metaphysical intelligibility in his terms through three key concepts: holism, information, and mind. Here's what Bohm says a long time ago, very early Bohm. The entire universe must be regarded as a single indivisible unit in which separate parts appear as idealizations, permissible only on a classical level of description. Then much later, he writes, we may regard each of the particles constituting a system, particles in scare quotes there, as a projection of a higher dimensional reality, rather than as a separate particle existing together with all the others in a common three-dimensional space. Ultimately, the entire universe, with all of its particles, again in scare quotes, including those constituting human beings, has to be understood as a single undivided whole, in which analysis into separate and independent parts has no fundamental status. So what underlies this holism? It's not just a free addition. It's not something made up on its own. The holism is not, though, underlaid by causal relations. Causal relations must be derivative of some deeper interconnection. We know that there are connections in quantum mechanics that are not explained by causation. So instead, we have active information. And this is, I think, the availability of real information. I'll say what I think that means in a minute. The availability of real information to everything about everything. And nothing happens without accessing this universal pool of information. But active information is not what information theory studies. Bohm and Hiley call this sometimes Shannon information. Shannon information is not active information. Really, it's only a kind of information that this Shannon has a theory of transmission of information, not a theory of what information is. In the case of Bohm, it is genuine semantic information, which carries intrinsic meaning. If we go back to the Bohm tester, the very counterintuitive way of finding out whether you have a good bomb, even though if you interact with the bomb, it will explode. Why does this work? Well, this works because the information that a witch path detector, that is a good bomb, the information that a witch path detector provides is also available in the other path. And this is not a causal link at all. The arms could be spacelight separated, and the bomb could be added. In principle, it would be a hard job, right? But in principle, the bomb could be added after the particle is in one path or the other. So this is completely different from the Shannon information picture of a bit channel, but more like a pervading field of semantically significant information that informs the system. In fact, Bohm and Hiley use the traditional terms of form and matter to illustrate what they mean here. The quantum potential is kind of like the form which matter can take. Now, finally, where do we find semantically significant information? I would argue there's only one place, and that's conscious mental states. Although, to forestall some misunderstanding, by conscious, I mean something very minimal, really nothing more than experience, not self-reflective, not awareness of one's own states, just this more basic experience itself. There's been a lot of confusion about this because there are many ways to define consciousness, and many do regard consciousness as a kind of high-level mental feature, which involves self-reflection upon one's own mental states. That's not what I mean here. I mean just the basic activity of feeling, the sense of being alive, maybe something like that. Everywhere else, except in these mental states, all you have is Shannon information being transferred back and forth between systems. And that information requires interpretation by us to be seen as information at all. Bohm and Hiley put it, for them, active information is for the system and not for us. Information for us is what we interpret, what we put onto some system. If you're watching a bit stream between two computers, maybe you could interpret that as meaning something. That's information for us. Probably not information at all for the system. The system is totally unconscious. Active information is what's for the system itself. Bohm writes, reality can be considered as, in essence, a set of forms in the underlying universal movement or process. Thus, the way could be open for a world view in which consciousness and reality would not be fragmented from each other. And he goes so far as to say, the particles of physics have certain primitive mind-like qualities, very Leibnizian sort of thing to say. Highly explicates active information explicitly in terms of mentality and consciousness. Here's a quote: if we now interpret active information by assuming it has both a phenomenal and a physical aspect, we have a concept of information which is both concrete and fundamental. So now, obviously, we've circled back to Leibniz again. Bohm finds a soul-like aspect to the material world, and this aspect underpins the world, joins it together. Unlike Leibniz, I don't think it's an idealist vision, but it does emphasize this thorough interconnection in the field of conscious information rather than the Leibnizian windowlessness. You remember, for Leibniz, every monad is independent, completely independent of all the others. There's zero interaction. That's a very strange picture. You ask why do you need more than one monad? But anyway, not so for Bohm, Hiley, and his followers. This is a real interconnection. It's not just a causal interconnection. And this provides us with our metaphysically intelligible account of how the quantum world would work. Well, that's all good. Let me end, though, with a final slide with some worries. Are we not still left with the basic unintelligibility of quantum mechanics? Quantum mechanics is just inexplicable. Well, that's one question. Why does adding this interconnectedness give us quantum mechanics? Why should it? Why not a classical world with interconnection? Why not a super quantum world? The correlations found in quantum mechanics, which are non-classical, could be even stronger. Apparently, there's this bound of the maximum level of correlation between entangled systems, which is not the maximum amount of correlation there could be. So you ask why that. Even the mechanists, if only they had known about quantum mechanics, maybe they would have said, well, why aren't we in a quantum world? Well, these questions seem to remain kind of unanswered, but maybe we're getting close to something that is truly unanswerable. Leibniz is famous for saying the number one philosophical question is, why is there something rather than nothing? He thought he could answer that. Very few people have followed him in that, but there's a question maybe you cannot go beyond. And maybe we're getting close to that. And having our metaphysically intelligible quantum mechanics should be enough for us. And I will stop there. Thanks very much. Sorry for going on.
Oh, that was fantastic. Thank you so much, Bill, for your wonderful presentation, spanning from millennia, really, from atomism. So yeah, thank you so much for that. We can, of course, now open up for questions. If you want to ask a question, you can use the raise your hand function under reactions at the bottom of your screen, or or write your question in the chat. If it makes you feel more comfortable, I can read it out for you. I can already see that the chair of this event has his hand up. So Pavel, please come in.
All right. So yes, thank you very, very much. Very, very interesting, and lots of new interesting ideas there as well. And but I just thought I'll ask a little bit about this question of intelligibility, because I do remember when talking with Bohm quite a bit about the ontological interpretation or causal interpretation in the 80s. He would emphasize intelligibility, and he would accuse the Copenhagen view or other that they are not really intelligible, and that's so he saw himself. I think he thought that what he's trying to do with what he then I think called the causal interpretation is precisely intelligibility. And of course, one might think there that even the way they want to explain that in the papers, that this idea of active information as sort of something that almost like enters the energy of the particle, and then the particle responds to that. One could always ask to what extent that is going towards some sort of Cartesian mechanistic model. Of course, it's not mechanistic in the way you pointed out, because there's non-locality, but in some ways, it seems that this is also something that Bohm was kind of struggling for, and this was like a selling point of the interpretation, that you would really get a picture of or model of what is actually taking place, and that is of course something there, and I guess the other point is just that to what extent that kind of striving toward intelligibility takes you toward a more mechanistic picture, which in some sense was in contradiction with this more non-mechanistic view he wanted to advocate. But I don't know, I just wonder whether you thought about that. I sometimes thought about that, like, what Descartes would have thought about the Bohmian picture of active information, and where you can use a radar wave analogy to kind of illustrate what might be going on.
Yes, I know they talk about the autopilot analogy, right? So the ship that steers itself, and of course that does suggest causation. And there's a whole branch of Bohmians that do go along with this causal interpretation of his view. But it seems to me, as Bohm evolved his views, the holism became more important. The separate, I guess you could say, when Bohm begins, the original paper, you could say, yeah, the world is made out of particles. What a relief, right? It's just like we thought, it's made out of particles, but they have this weird interconnection thing, right? But later on, he seems to say, no, the idea of separating the world into parts like that is somehow flawed. It's the wholeness of the holism. That's the lesson of quantum mechanics that's more important. I don't know enough about Bohm's views to really say how his thought evolved over time here. It has seemed to me that the 52 paper was not presented as, this is what I believe. It's presented as, here, you said there couldn't be hidden variables, but here's a proof of concept. And then the actual views that he developed went into took holism as the guide and not the possibility of the particle picture. I don't know, does that seem something right to you? You talked to him.
Yeah, well, this is a tricky thing. I think it might be partly just part of his personal history, or even psychological, in the sense that I got very strongly, I got the sense that in the 80s he felt that this theory hasn't that wasn't given its proper attention in the 50s. So it was like a child that had been neglected. And he very much, that's why he kind of very much wanted to promote even a new version of this, the 52 theory. Of course, with all the new ideas there, but somehow I think that he felt that, so it wasn't always the holism that, I think he was also worried about the non-locality. I think Basil would tell us stories about that Bohm was sitting on the fence, and then Basil would ask him, David, is quantum mechanics non-local? And then Bohm would say, yes, it is. But it's not an easy, because then it does raise all kinds of issues with the relativity and those kinds of things. So I think in that sense, of course, it's in the case of Bohm, because he worked with these many different schemes. Of course, you can always find relationships within them, but I sort of felt that there's something. He was keen to have these physical models, and the same thing goes for the 1951 book, the textbook Quantum Theory, which he wrote when he was still in some ways with the Copenhagen view, and Niels Bohr, Wolfgang Pauli. Even there, he very much wanted to have a physical picture as opposed to mathematical formalism, which was the tendency then. And there again, I can see, so he was for physical intelligibility, physical notion, sort of something people could understand. And that, I think, often what happens if you do that, that will pull you perhaps toward to more mechanistic picture, which is then might be a little bit in contradiction to, in the case of Bohm, his utter intuition, which you're quite right about wholeness, and there are many, wholeness and the implicated order is very much emphasizing that aspect, and of course he did see that also in the causal interpretation, as you gave some of the examples here. But I personally, I just find that as a sort of a kind of a, whether the price, what kind of intelligibility are we looking for, and where does it take us, and what is the and what I thought was interesting in your slides, when you said, in the Leibniz slides, he said mechanically that is intelligible, or how Leibniz connected to be mechanical and to be intelligible to each other. And I can see that's one way of reading Bohm, also to see how those two things together. And I could say, of course, the other question is whether there could be a new kind of rationality, a new kind of intelligibility, which would be more holistic, and somehow then we would have to start thinking in a new way. And that is, of course, perhaps what he was striving toward as well. But anyway.
Yes, your remarks make me think that maybe we could make Bohm closer to Leibniz, in the sense that Leibniz says, okay, the physical world has this mechanical vision, but there must be something underpinning it. And maybe Bohm could be seen somewhat similar. Yes, the physical world we can picture as particles interacting. I showed how to do that, but it does nonetheless need this underpinning, the holistic underpinning. That would bring them a little bit closer together. Yeah. That'd be nice.
Yeah. Thank you, Pavel, for this discussion. Of course, if you have anything else to add, please feel free to come in. Next, we'll go to Wendell.
Yes, if there is such a thing that we commonly call God, what could it be made of? Now, I'll use the word it rather than he or she, because that's ridiculous.
Well, I don't think I could give an answer. Leibniz has a nice answer. For him, God is made out of the same as our own minds. So mental substance, that's what God is made out of. So for Leibniz, God is a conscious being, has no physical aspect. And Leibniz thinks, okay, I can understand the existence of independent minds. That might be a hard thing. But he takes that from Descartes. But the whole idea that minds could be independently existing things, no need for a physical embodiment. Leibniz goes along with that, and then God is, so I think he calls God the supreme monad. And we share with God consciousness, thought, and like. That's probably the best answer for what God can be made of, I can think.
Well, is it possible that it could be made of subatomic particles?
Well, some conglomeration of particles would seem to be non-eternal. God is supposed to be eternal, perfect, unchangeable in some ways, and assemblages of particles, especially the way we now think of them, are always in flux, and that doesn't strike me as being very godlike. Maybe you disagree.
Okay, thank you.
Thank you, Wendell. Just to allow new people to come in, I'd like to invite Claire in.
Yes, I'm so moved by this topic and by your presentation. Can you hear me?
Yes.
Yes, okay. In 1986, I finished my master's thesis. And in that, one of my references was David Bohm's book, Wholeness and the Implicate Order. And another part of what I studied was Kashmir Shaivism, which is an Indian philosophy from India. And so what I would like to do is to read 2 sentences to you of the Kashmir view and ask you, how does this fit in with what you think? So the first sentence is, its major premise, Kashmir Shaivism, is that there is only one ultimate reality, that's a capital UR, and that this reality has 2 aspects, one transcending the universe and the other operating through it. Says something about cosmic evolution, but the second sentence is, Kashmir Shaivism accepts the fundamental premise that capital P, capital C, pure consciousness is the basic substance of the universe. And they use the word, I mean, they don't use the word God, but they do use the term cosmic consciousness with 2 capital C's, which they say it's like qi in the Chinese version, or ki in Aikido, the energy of the universe. But anyway, so I'm not sure what my question is, except I'd like to hear your response to those sentences. Thank you.
Well, the idea that there's one reality with 2 aspects is a possible view, dual aspect monism, it's called. I think people like William James were not trying for that. And what you read seemed a little bit in tension with itself. So the one, you have the 2 aspects picture, and the other is pure consciousness is all. Pure consciousness, of course, it's hard to know what exactly is meant by that, but I take it, I'm not sure what it is, but I can't say what pure consciousness is, but at least I can see that there's these 2 different ways of viewing. One is, okay, there's 2 aspects to something. And the other is, no, there's one. There's only one, the pure consciousness. Maybe it can be interpreted in different ways. That's a bit like William James's picture, I think. I think I might be more attracted to that side of it than the double aspect side.
I think, thank you. I think what they're talking about when it says pure consciousness is the basic substance of the universe, is that everything comes out of that, which makes it's like the enfolding and the unfolding to me. That's how I think of it.
Yes, that's another picture, which is that it's somehow an ontological basis. But again, it's the same tension, because the other side is nothing comes out of it. It's what is, right? It's all there, so to speak. So again, it's like two different ways of thinking about this. One in terms of something producing or something merely being. And I think I kind of like the mere being, pure being side of it.
Yes, that reminds me of something something related to this, that in Kashmir Shaivism terms, I remember in a lecture hearing this, that in their view, if you want to use the word God, but whatever, like I learned in Sunday school that God created the world, out of something. And in the Kashmir Shaivism view, they said it became the world. It became the universe, which is like that's the most monistic sentence I think I've ever heard. And it's so hard to talk about it in words.
Words. But that would be the difference, right? One where there's an act of creation that produces something else, so to speak, versus it's all.
Oh, he may have his internet may have cut off. Sure, he'll be back soon. But Pablo, did you have anything to add?
Well, yes. Maybe we'll
Reading the Bible is.
Yeah, wait for Bill. Bill is there, right?
Oh, am I gone?
Yeah, you were gone.
Am I back?
You're back
You
now.
seem to be back. Yeah. Or then we are in another branch.
Anyway, I see my video is frozen, but you can hear my voice.
Yeah, and we can see. Yeah, I thought we could go back a little bit to this, as you were talking about this information and active information, because Bohm used to also give the DNA molecule as an example of active information. So perhaps not just as an analogy, saying that the DNA is also information for the cell. So it's not information for us. So I guess he wasn't thinking of that as Shannon information, but rather as some bit like the quantum information. And so what do you make of that? I mean, is that then, does it mean that the DNA, that system has to be conscious then, or how do we think about that?
Well, if you take this very minimal notion of consciousness, so I know David Bohm he says there's a mind-like aspect or mind-like feature to nature, all parts of nature, but denies that they're conscious. But I think, well, I'm not 100% sure, but I think probably he was thinking of consciousness as this rather more sophisticated cognitive state that many people, that's what they think consciousness is. Mm-hmm. Whereas by consciousness, I mean just this basic elemental feeling or phenomenal experience. And there, yes, information for the system, I guess, does go with some kind of this primitive phenomenality. So it's not like the DNA molecule is thinking, is my life worthwhile? Our problems of consciousness, but it has some kind of phenomenal aspect to it.
Okay. Thank you. Pavel. Next, we'll go to Kathleen.
So just following up on that last conversation, actually, thanks, James. It's a great kind of foray into my question. My question is, what is your view on the possibility that Bohm did not separate ontology and science/physics?
Well, it's a good question. And certainly he wanted, it's obvious, right, that he was reading off some of these metaphysical views from the way the science was developing. So it's the quantum holism stems from the formalism of quantum mechanics. And that seems to be one of the inspirations for that. So there he brings them together. So I think he would say, yes, the world, when we investigate it closely enough, the world will reveal these, if you like, metaphysical features. And science is then a doorway into them. It is pretty amazing that the advance of science leads us to a theory where you have these strange interpretive problems, which seem highly philosophical.
It's interesting because I'm not a physicist in any way, shape, or form. And yet I experience, when I read Bohm and listen to all of these dialogues, I experience him much more as in a non-physicist, non-scientific, non-mathematical way, and yet understand it from an ontological perspective. And I'm curious about that because, of course, he had the relationship with Krishnamurti as well, right?
Yes, I know little about that side of Bohm, but there's no doubt that this was a very large part of his intellectual development.
Mm-hmm.
Can I ask, jump in and also ask this same question here is that, because in philosophy, one of the big questions is what Bill already has sort of raised, is that how much of our metaphysics we can read from science. And somebody might say that every scientific theory is based on some assumptions that we put into it ourselves. So in a way, a critic might say, well, we should be careful when reading our metaphysics from science, because maybe all we get from there is what we actually ourselves have put in there. But there's still somehow being aware of that. Then the interesting question is whether science gives us some objective input, like things like non-locality or just what Bill was saying, and maybe I could ask Bill, what is your view of the situation in philosophy, that how much are philosophers actually interested and able to listen to what science is trying to tell us about metaphysics or ontology?
Well, that's a difficult question. The philosophy of physics is a thriving enterprise, which is pretty close to physics nowadays. So a lot of philosophy of physics is highly mathematical and pretty remote from traditional philosophical concerns. I just think it's so strange what you were saying about what we put in terms of metaphysical presuppositions to the theories that we make. And that is exemplified perfectly by the mechanical philosophy. So there they started off and they said, yeah, obviously the world is made out of little tiny bits and pieces. I mean, we can sort of see the pebbles on the beach and all this. And they try and do that for a few hundred years. And nature comes back and says, no, that you're completely wrong. You cannot make a theory where nature is made out of just a bunch of independent bits and pieces. So there we had this, I think, rather ingrained picture. And it turns out you can't make the world be that. That's just amazing that that's the way it worked out.
I will say this, and then I'll pause, let somebody else. But I do think, let's see if I can articulate this properly, that it's what you're saying is interesting in the sense that from an ontological perspective, the experience, I can say I experience what you're talking about, but I might not be able to explain it, which is the challenge of ontology at many levels. And yet it's possible, even in my own work, I see this, it's possible that the work that we do is actually an expression of the implicate to explicate order, but we don't have the mathematical or physics lens to give it that explanation. And yet it's there. It is happening. We are that design as human beings.
Yes, it is interesting that quantum mechanics teaches us that you can look at one side of the phenomena or another, but you'll always be leaving something out when you do that. That nature is not fully sort of explicative, right? There's always this implicate order behind.
Mm-hmm. Yeah, they're actually, well, from an ontological standpoint, they'd be not separate. They'd be integrated, for sure.
That's right. And so you can draw out one aspect. So you just say position and momentum, right? Yeah, you can look at the position of the particle, but then you're leaving aside and cannot measure the momentum. Not that it doesn't exist or isn't an element of nature, but it's not accessible if you've chosen to measure position. That's really interesting.
Thank you, Kathleen, for coming in. We'll next go to Niels. Oh, still muted, Niels. There we go.
That's better now. I really enjoyed your laying out of all these possibilities of interpretations and stuff. I only discovered Bohm fairly recently. I'm something in physical sphere. I have developed intricate models of pedestrian movement and general transportation modeling, because it's got many of the things that goes on in that has a parallel to what Bohm is doing. And for many years, I looked into to try and find someone else who had a similar perspective of how reality and how things function together, the interaction and all this stuff. And when I came to Bohm, and also Rupert Sheldrake, there was a dialogue between Bohm and Sheldrake in one of Sheldrake's books about the new science. And that was really inspirational. So I come from a different perspective where I can see, I have an ontological and metaphysical model that can be used to assess various aspects of interaction and information, so that what is going on, if we take something like graph theory, I know that Leibniz was interested in that aspect of things, how things relate in networks and things. And also Euler is supposed to be the one instigated what we now call graph theory. And for some reason, I managed to extend that into something I could see that could fill a universe with how people can move and how things can move, and then interact as well. So it's a complete model in that sense. So I still feel that Bohm was right in the wholeness aspect, because unless we can spread out the whole world, whatever we mean by world, I mean, the world could be the transport world, so to speak, and that could be complete in that sense. That could be a global thing. So I'm very interested in Leibniz, because it's a graph theory. This is about relationship and about reasoning. And so at one point, long before I knew Bohm, I was forced into a point where I could say that we can define what we could call a global transport system, which we could call the universe of transportation, where everything would work in parallel. So
time is rather short, so perhaps
yes,
Bill,
I know.
Do you have some ideas about this Leibniz ideas about network or graph?
Yes, I think what I'm suggesting is I think relates to Leibniz way. So this is purely mechanical, but then it's also quite complex in the way that every mover has a free will and can do whatever he wants. But if you want to optimize that so that you make equality for every operator in this universe, then and that is possible to optimize that. And that, for me, that you need an outside mind who can see everything, who can incorporate everything, as in a sense could be reflected back from the individuals in this global network of world.
Yeah.
Well,
you certainly inspired me with what you, and especially. Well, what would you recommend in order to understand Leibniz better?
Oh, well, there's a place called the Stanford Encyclopedia of Philosophy.
Oh yes, I've dipped into that in many circumstances. Yes,
so
I know that.
A guy with the last name Look, L-L-O-K, has a great article about Leibniz and monadism. The idea of graph theory, a generalized graph theory, is interesting because, of course, you wouldn't have to have the nodes causally connected. They could have other forms of connection, which could be modeled by the graph theory. It'd be quite neat. There are people who use quantum formalism to study non-quantum systems.
Yeah.
And maybe something like that could even be done for traffic patterns.
Thank you, Niels, for your contribution.
Thank you for your inspiration. Thank you.
As we have just under 5 minutes left, I'd just like to sort of bring it back a little bit to intelligibility. And I had a question for you, Bill, which was, during your presentation, you mentioned that, the mundane intelligibility, we've sort of lost it just because how complex and counterintuitive quantum physics can be. My question for you is, how important is it to keep a mundane intelligibility? Like, how important is it that the man on the street understands these complex scientific theories? Just because I'm more concerned about the dangers of this, just because I know that currently there is a bit of a suspicion towards the experts, and a couple of years ago we had the Flat Earth Society was speaking out. So my question is that how important is it that the man on the street understands these complex theories?
Well, I think it is important that there be a kind of physical significance to these theories that can be communicated to anyone with reasonable intelligence. I don't know if flat earthers would fall under that. So there should be a way to describe what's happening physically. This seems to be getting more and more remote, however, from the mathematical features of the theories. There's a funny cartoon by a guy, what's it called, XKCD, an internet cartoon. And one of his cartoons is Theories of the Atom. And he goes through and draws little pictures of, the old-fashioned theories. But he ends up with a very small ball surrounded by math, right? That's what we're left with for our theory of the atom. Very difficult. I think traditionally, the proverbial man in the street, it's the fruits of science that generate the respect for science. And I think, I'm speculating, I think that's sort of one reason why the exotic physics is less respected now than it used to be. I think it'll be difficult for physicists to get money for new super colliders. And kind of the reason it crudely put is, well, what have you done for us lately? Yeah, the atomic bomb, that was good, right? But what have you done lately? Like, it does seem kind of funny that modern physics is losing core particle physics is losing any connection to technology. And that, I think, is what makes people kind of think, yeah, science is important, or this part of science is important. And I know the math I can't understand, but since it made my iPhone, right? This is why we should respect it and pay attention to it. Yeah, but so science more and more is turning into magic. People think, yeah, I have no idea. I have this little box in my hand. I have no idea how it works. It's just magic.
Yeah. Great. Well, thank you, Bill, for answering my question. Of course, thank you for this session. I know we're on top of the hour, but do you have anything you want to leave us with to close this session?
Just thanks again to the Pari Center, and I'm so glad to have discovered the existence of such a place.
Oh, great. Well, thank you, Bill.
Thanks for everyone for coming.
Thank you. Yes. Thank you, everyone, for joining us and for contributing through your comments, questions, or just by being there. And of course, thank you again, Bill, and thank you, Pavel, for coming in and contributing yourself. Just before we go, I'd just like to invite you to next week, which is the last weekend of this part of Beyond Bohm. On Saturday, we will have a session entitled Why Bohm Was Never a Determinist, which will be, we will have Margie van Strien as speaker. And then on Sunday, we will have Marja Lisa Kakuri-Knotila talking about Aristotelian metaphysical and epistemological reflections in David Bohm. So I hope to see you then. I'd also like to invite you to this free session that will happen on Wednesday, which is with Alex Gomez-Marin in conversation with Professor Avi Loeb, part of the series, The Future Scientist. where they will be discussing reproducibility of science and anomalies, which are rare but relevant events that can help rather than hinder scientific progress. So I hope to see you then. If I don't, otherwise, I'll see you next weekend. Thank you again, everyone. Thank you again, Bill, and we'll see you again soon here at the Bar Center.